fluid coding, and AI. The scary part of auto-research is not that an agent edits code, it is that the agent knows when to throw its own code away. Karpathy showed the minimal version for LLM training. Pi Autoresearch turns the same loop into a developer tool for normal repos. Here is the core idea in one sentence. An agent makes a small change, runs a benchmark, reads a number, keeps the change if the number improves, and reverts it if the result gets worse. That sounds simple, but it changes the role of the coding agent. It stops being a one-shot patch generator and starts acting like a tireless lab assistant with Git, logs, and a scoreboard. Karpathy's Autoresearch repo is deliberately tiny. The important pieces are a fixed preparation file, one mutable training file, and a human-written program file that tells the agent how to run experiments. The agent is not asked to redesign everything. It edits the target training file, runs a fixed 5-minute experiment, measures validation bits per byte, and keeps only the changes that improve the score. That 5-minute limit is doing more work than it first appears. The agent cannot win by making a model bigger if the model trains too slowly inside the budget. The metric is not absolute model quality. It is the best result under a short, repeatable constraint. The constraint is the product. It turns research into a tight optimization game where every idea has to pay rent immediately. The public results are interesting, but they need careful framing. In one Karpathy started overnight session on an H100, the report shows validation bits per byte moving from 0.99790 to 0.969686 across 1.69686 across 1.2 were discarded, and one crashed. That is evidence that the loop can find useful improvements. It is not proof that every short-run win transfers to every model, every dataset, or every hardware setup. The same pattern also shows up in Karpathy's NanoChat leaderboard. A time-to-GPT-2 leaderboard entry moved from 2.02 hours to 1.80 hours with Autoresearch Round 1, then to 1.65 hours with Autoresearch Round 2. That is a first-party leaderboard, not a complete causal study. Still, it shows why developers paid attention. The loop was not just producing patches, it was finding accepted improvements in a measurable training race. Pi Autoresearch generalizes the pattern. Instead of being locked to one LLM training file and one loss metric, it lets a terminal coding agent optimize almost any repeatable codebase number. That can be test speed, build time, bundle size, API latency, Lighthouse score, or training loss. The key requirement is not that the project is machine learning. The key requirement is that the goal can be measured over and over. The useful part is the repo-level contract. Pi Autoresearch uses a human-readable plan file for the objective and prior attempts, a shell command that prints parsable metrics, an optional checks command for tests or lint, and an append-only JSON lines log for every run. The agent is not remembering because the chat is long. It is remembering because the repo has a ledger. Shopify's engineering post is the best bridge from model research to regular software work. The first version of the Pi extension focused on Polaris build time. The post reports a 19.1-second baseline, repeated hypotheses, benchmark runs, and a kept result that made the VRT build 65% faster. The important part was not a glamorous AI trick. It was removing wasted pipeline work and narrowing TypeScript transforms. Shopify also reported a liquid codebase run attributed to Toby Lucky, 53% faster combined parse and render time, and 61% fewer object allocations. But the caveat matters. The report itself says it was probably somewhat overfit, while still containing useful ideas. That is the right mental model. Autoresearch can surface strong candidates. It does not remove the need for engineering review. The whole loop is powerful because the metric is the boss. That is also the danger. If the target is wrong, the agent will optimize in the wrong direction with impressive discipline. A test speed objective can be gamed by skipping work. A build objective can be gamed by deleting expensive files. A noisy benchmark can crown a fake winner. The agent is obedient. Your measurement decides what obedience means. Pi Autoresearch tries to reduce that risk with guardrails. It supports optional checks after benchmark improvements, so a faster result still has to pass correctness pressure. It also uses confidence scoring after multiple experiments with median absolute deviation as a rough noise estimator. That matters when the claimed improvement is smaller than the benchmark jitter. Tiny wins should be retested, not automatically trusted. The practical recipe is boring, which is why it works. Pick a measurable bottleneck. Write the shortest benchmark command that still reflects reality. Print one clear metric line. Add tests, type checks, or lint as backpressure. Cap the number of iterations and the spend. Keep every run in a log. Review the kept commits before merging anything. Autoresearch is not magic. It is disciplined optimization with an agent doing the repetitive parts. So the verdict is, treat Karpathy Autoresearch as the minimal proof of the loop, and treat Pi Autoresearch as the practical developer version. Use it when the objective is measurable, the benchmark is stable, and the final diff can be reviewed by a human. Do not use it as a replacement for taste, product judgment, or correctness. The best use case is boring performance work with a real scoreboard. If this helped you understand why Autoresearch matters beyond model training, like the video and subscribe to Fluid Coding and AI. More agentic coding breakdowns are coming, focused on the tools that actually change how developers build.